Okay, so welcome back to next class of the ionic reactions, and we were completing the series of lectures for chemical dynamics, and in the last classes we have discussed in brief the ionic reactions, the rate of ionic reactions, and we have tried to understood how these ionic reactions are occurring based upon the double sphere model and the single sphere model, and we actually reach to the consequences of ionic reactions. And in the last classes we have discussed when the activated complex is formed from the ions, if the charge on the activated complex will increase or decrease, what will happen to the entropy of the system. And we were talking about the electrorestriction. So these processes which we were discussing about. Now the thing is that in the next class, in this class we will discuss about actually dielectric constant, the variation of dielectric constant. Okay, so this is the second consequences which we will discuss now. But the thing is that key we have considered arbitrarily that during the double sphere model, single sphere model, we have just considered that the solvent molecules are evenly dissociated, uniformly dissociated, and as the dielectric constant is the property of the solvent molecules, so we were saying that dielectric constant would have similar value at every point of the solution phase. Wherever and whenever you will consider the solvent molecules that would give same value of dielectric constant we have considered in the last classes and during the calculation of double sphere model and also single sphere model also. But in the last class, first consequences which we have discussed, we have come to know that okay, some solvent molecules get associated with the ions and some solvent molecules are free. That means the distribution of the solvent molecules is not completely uniform or completely even in the solution phase. Rather, it is different. Near the ion, it is different, and far away from the ion is different. When it will form the activated complex, the distribution would be different, and when it not forming the activated complex, the distribution is different. That means throughout the course of the reaction, the structure of the solvent medium actually continuously changes. This is not uniform throughout the reaction medium. Therefore, the consideration of the dielectric constant to be constant at every point of the reaction, at every point of the container, it would be not be a correct statement. So before going deep into this particular topic, we actually need to understand what D is actually mean by dielectric. What is mean by dielectric? We have actually introduced this dielectric term during our high school classes or 9th or 10th classes, or in the plus 2 classes when we were discussing about the electrostatics. But briefly, this dielectric term should be taught whenever we were talking about the parallel plate capacitor in our physics classes, in our graduation or plus 2 classes. So what is actually dielectric? And we actually know that larger the value of the dielectric constant, greater is the decrease in the value of greater is the decrease in the value of electrostatic forces of attraction existing between the ions. And if more solvent molecules of larger dielectric constant is introduced in the electrolytic solution, then the ions in between the ions, the solvent molecules of higher dielectric constant will come in between them, and they will act as an insulator, and they will decrease the electrostatic forces of attraction between them. The ions will become more and more free, or they get dissociated. This we have understood in our plus 2 classes and also our plus 3 classes also. But actually, is really this dielectric acting as an insulator, or something else is there that we need to understand, that we need to address? Actually, what is happening, let us say simple two ions are there. And obviously these ions will be associated with the solvent molecule. For the sake of simplicity, let us consider this is associated with the solvent molecule, and that is having a charge separation, partial charge separation occurs in that particular solvent molecule, and obviously the positive ion will be associated with the negative dipole of the solvent molecule, and whereas the negative ion will be associated with the positive dipole of the solvent molecule. For the sake of simplicity, I am considering only a single solvent molecule. Okay. So before, let us say now no solvent molecules are present in between them. Okay. Now if cation and anions are there, it is a charged particle, positive charged particle, it is a negative charged particle. So obviously there will be an electric field generated by the ion. What is the electric field? Electric field is that area around a charged particle where a charge can, where any other charged particle can experience the influence of that charged particle. That is the electric field. An electric field do consist of electric lines of forces. So let us say ki these are electric lines of forces. Similarly, these are electric lines of forces. Okay, and these are nothing but the electric field, the area of influence of that particular ion. This is electric field. Okay, so now let us say this ions is entering in between the cation and anions. Okay, now let us just differentiate them. This is the thing. Okay, so now what will happen? This is negative dipole. This is the negative dipole. So as the electric lines of forces moves from point positive charge to point negative charges, so in the solvent molecules what will happen? Here also a electric lines of forces is actually will be directed. And this will be directed in this particular direction. Okay, so what is actually happening? It is very interesting that the electric lines of forces created by the ion is acting in this direction, but inside the solvent molecules the electric lines of forces, this is in the ions and this is the solvent molecules, this is acting in this particular direction. So what will happen as a result of this? As a result of this, you can consider the electric lines of forces are acting in opposite direction. So what will happen? As a result of the entry of the solvent molecules, the electric field between the ions decreases. Why? Because solvent molecules compensates for the electric field. What do you mean by compensates? What do you mean by compensates? Compensates means the direction at which the electric lines of forces were acting upon, in the opposite direction the electric lines of forces created by the solvent molecules is acting upon. That means the effect of electric field generated by the ions is actually decreases. Electric field intensity actually decreases. That means solvent molecules decreases the net electric field intensity between the ions. Therefore, if the electric field intensity will increase, what would happen to the electrostatic forces of attraction? Obviously, the electrostatic forces of attraction between the oppositely charged ions would decrease, and therefore the ions will become more and more free with further alignment of the solvent molecules in between the ions. That is, if more number of solvent molecules will come in between them, the more number of electric lines of forces get dissolved or get diluted existing between the ions, as the solvent molecules is creating a opposite electric field, which would decrease the influence of the electric field created by the ions, which would decrease the electric field intensity. As a result, the electrostatic forces of attraction existing between the ions decreases. Therefore, the ions will become more and more free. Okay, and if the solvent can able to decrease this electrostatic forces of attraction to a larger extent by creating a larger electric field in between them, then the value of that particular solvent of the extent of decrease of electric field between the ions will become more and more high. As a result, the ions will become more and more greater. So what will happen? Therefore, we can say कि the solvent medium, the solvent molecules which would have a higher dielectric constant value, they actually decreases the electric field existing between the ions to a larger extent, and therefore their dielectric constant value will be larger. So now, if we will not take any polar molecule, these are actually polar molecules. But if we take the non-polar molecules, what would happen? Non-polar molecules, what would happen? Actually, in the non-polar molecules, there is no charge separation. So when these non-polar molecules will be entered into the cations and anions, in between the cations and anions, at first there will be generation of the dipole due to the instantaneous dipole. So obviously Here also there will be a creation of electric field in the opposite direction, but the magnitude of electric field generated in this particular solvent molecule will be very small, as initially there was no charge separation. Due to the presence of this cation and anion, the instantaneous dipole is created. So as the opposite electric field intensity is lesser, therefore the magnitude of electric field intensity will decrease, but that will decrease to a very less extent. Henceforth, the dielectric constant for this particular molecules is very less. Therefore, if you consider H2O, which is very polar in nature, that is having about dielectric constant value of 80, nearly about 80, but non-polar molecules, hydrocarbons, carbon tetrachlorides, that have a very lesser value of dielectric constant, because there is no presence of charge separation in the hydrocarbons or the carbon tetrachloride, and therefore what will happen, there will be very less presence of a inbuilt or intrinsic electric field will be there, and which would decrease the electric field acting between the ions to a very less extent. Therefore the ions will become free to a very less extent. That means the dielectric constant value will be very less in nature. Okay, so now we will take another case. Now let us say in a container I am considering two electrodes and I am keeping water molecules in between them. But initially when I have not put any, that means I have not connected this metallic sheets with any source of battery, or I have not applied any potential difference, then whatever the solvent molecules I will be placed here, that solvent molecules would have a random direction. They will have random direction. They can present in any possible direction. The alignment is not proper. This is the situation when I have not applied any electric field, or there is no source of battery I have connected with the electrodes. But once I connect this with the source of battery, the situation will change. What the situation would be? Let us say the situation would be very much different. Let us say this, after connecting with battery, this is positive charge in nature and this is negative charge in nature. That means here positive electric field, here negative electric field will be there. That means now I have applied the electric field. What will happen? Slowly, the solvent molecules will be directed in a particular direction. Near to the positively charged electrode, the negative dipole of the solvent molecule should be there. And near to the negatively charged electrode, the positive dipole will be there. But although after applying the electric field, when the voltage of the battery is very small, then the electric field generated in the electrodes will be very small. Therefore, it cannot able to align all the solvent molecules in a single direction. Therefore, some of the solvent molecules will also be there which will be randomly arranged, and therefore some of the electric field get cancelled out. Here, due to the random, what is actually happening, due to the random arrangement of solvent molecules, the electric field get cancelled out. Here also some of the solvent molecules are there. Which are randomly arranged. So, due to the random arrangement of solvent molecules in between the electrodes, the net electric field intensity get cancelled out, or the net effect decreases. But when you further increase the potential difference along the electrodes, what would happen? The electric field intensity will further increase, and which would direct these solvent molecules to get arranged or get aligned in a particular direction. As a result of which what will happen? More and more molecules will get aligned, solvent molecules get aligned with increase in the potential difference. So now the polarization actually decreases. What will happen? Polarization. That means proper orientation occurs. And when the proper orientation occurs, there actually the solvent molecules cannot now decrease the electric field intensity. Or initially, due to the random arrangement of the solvent molecules, the electric lines of forces are randomly arranged in between the electrodes. So they were cancelling out. Now when they are directed in a particular direction, the electric lines of forces will also be directed in a particular direction. Okay. As a result of which, what will happen to the dielectric constant value? The dielectric constant is that nature of the solvent is that nature of the molecules where it decreases the electric field intensity. So when the solvent molecules get directed in a particular direction, then obviously they cannot able to decrease the electric field intensity to a larger extent when they were arranged in a random direction. Therefore the dielectric constant value actually decreases. So when you will increase, what do you conclude from this? When you increase the electric field, or when you increase the potential difference across the electrodes, then the electric field across the electrodes increases, as a result of which the dielectric constant of the solvent molecules or the molecules will decrease. Okay. And this is the similar case which is happening in the, why I have taught this? Because this is the similar case which is happening in the ionic reactions also. So what is happening in the ionic reaction actually, let us say this is a reaction medium. This is a container where the reaction is going on. There will be ions. Let us say this is an ion. And there will be solvent molecules. They were present randomly. But just consider the solvent molecules which are present near to the ion and the solvent molecules which are present far away from the ion. The solvent molecules which are present very nearer to the ion, that means it is present nearer to the higher electric field. Okay, as we move from away from the ions, as we move far away from the ions, obviously the electric field intensity of the ions will decrease. Therefore, the solvent molecules which are present far away from the ions, they are randomly arranged. They are randomly arranged. But the solvent molecules which are present near to the ion, they are experiencing larger electric field. Larger electric field. Therefore, here the dielectric constant of the solvent medium would be lesser. But here the solvent molecules, where the solvent molecules are randomly arranged and which are experiencing very less amount of electric field, here the dielectric constant value will be larger. Similar which we have discussed in this parallel plate capacitor, when the electric field is smaller, the solvent molecules were randomly arranged and they can decrease the electric field intensity to a larger extent. But when the electric field intensity I slowly increase along the electrodes, the solvent molecules get associated in a particular or oriented in a particular direction, then they cannot decrease the electric field intensity. So therefore the dielectric constant where decreases. That means more and more the solvent molecules get associated with the ions, or more and more they get associated with the higher electric field intensity, the more solvent molecules will be oriented in a particular direction and the dielectric constant value will be lesser. And as we move from the far away from the ion, the solvent will experience lesser electric field intensity, they will become more and more random, and therefore they will experience lesser electric field intensity, and therefore the dielectric constant value will be larger in nature. So now we can say that key, after discussing some of the points, this is not needed to mention in your notes, but this need to be understood. After discussing this, we can understood that solvent is continuous. Solvent is continuous, but considering the change in dielectric constant in the neighborhood of ions occurs. Why? The solvent molecules nearer to the ions will be more solvated and they will be oriented in a particular direction, and the dielectric constant will be smaller. But the solvent molecules far away from the ion will experience lesser electric field, will randomly arrange themselves, and the dielectric constant will be larger. Therefore, we can write the dielectric behavior of a liquid is actually due to the orientation of molecules in an electric field, and at a very high electric field there is tendency of saturation. Saturation means the further there will be no change in the dielectric constant value, because the dielectric constant of this particular solvent will be very less and that cannot decrease further, and this is the case whenever they are present at higher electric field or near to the ion. And what is saturation? Dielectric constant approaches a lower limiting value. As the solvent molecules when becomes completely aligned in the field, there can be no further orientation. No polarization, and the dielectric constant has very low value, and which is the characteristics, and which substance has very low value of dielectric constant? Hydrocarbons. Which is the characteristics of hydrocarbons? And other non-polar substances. That means even if the solvent molecules, let us consider to be water, which would present very far away from the ion, that would have a value of 80. But when that solvent molecule will present nearer to the ion, that will experience so much of electric field that the dielectric constant value of that particular solvent, that is your water, will decrease as they will be directed in a particular direction or oriented a particular direction, and that would be near about the dielectric constant for the non-polar molecules also. In very short we will see how this is happening, and this effect where the dielectric constant value of the solvent molecules will decrease to a very low value, and there will be no variation of solvent dielectric constant value, then that is called as dielectric saturation. It is very important term, dielectric saturation. Close to the ion, close to ion, the electric field is very high, and the dielectric constant is very much lower. than in the rest of the solution. It has been seen that close to ions, the dielectric constant is seen to have a value of 1.78. This I am talking about the water molecule. Close to ion, it is about 1.78, and it rises quite steeply. There is a sharp increase to a value of 78.5. That means near the ion it is about 1.78, and far away from the ion it is about 78.5. Let us say a graph. Before that, due to the modification in the dielectric constant, the electrostatic interactions between ions in aqueous solution at short distance significantly different from what there would be if the dielectric constant had a value of 78.5. Okay, and you already know that from the double sphere model and also with the single sphere model that your Gibbs free energy of activation electrostatic contribution is a ZAZB square for 1 mole is epsilon DAB. That means this is inversely proportional to the dielectric constant. That means if the dielectric constant value varies in the solvent medium, that is near the ions that the value is different, and far away from the ion the dielectric constant value is different, then obviously the Gibbs free activation of contributed due to the electrostatic interaction will also be changing as the solvent medium is changing its dielectric constant value. That would what I want to say here. Therefore we can write the free energy increase in bringing ions together is increased by this effect. Why? Because greater they will come closer to each other, greater will be the solvent molecules will come closer to each other, and greater the solvent molecules will be experiencing greater electric field, and they will be oriented more in a particular direction at a larger extent. So what will happen? The dielectric constant value would decrease, and what would happen to the Gibbs free energy? Free energy of activation, or due to the electrostatic contribution, that would also increase. Effect. Particularly when the ions are brought to within a few angstrom of each other. Okay, let us see the variation. Okay, so let us say this is the distance from the ion, and the value is written in angstrom unit. This is 2, 4, 6, 8, 10, 12, 14, 16, so and so forth. And this is actually value of dielectric constant. How this dielectric constant is varying the distance of the ion. This is 10, 20, 30, 40, 50, 60, 70, 80. Obviously this is the limit. This is the maximum value of the dielectric constant for the solvent for the water molecule. And the minimum value is here 1.78 dielectric constant. Okay, so let us take another pen. Now when the value is around 2, when the solvent molecule is present very nearer, obviously the dielectric constant will be very small. But as we move far away, the solvent molecules will move far away from the ion, then what will happen? The dielectric constant value will increase. The dielectric constant value will increase. Here we are seeing a increase in the value of dielectric constant, and when it is present as very far away, the maximum value of dielectric constant will be observed, and that is equivalent to about 78.5. And here the charge on the ion is about Z equal to 1. Similarly, For about z is equal to 2, we are observing a similar type of curve. We are observing a similar type of curve. And for z is equal to 3, observing the similar type of curve, but just observe the for how much time. If the charge on the ion is very high, for how much distance the value of the dielectric constant for the water is remaining very small. That means up to 8 angstrom, the value of the solvent medium is about 1.78 when the charge is 3. That means how the charge on the effect has a effect on the value of the dielectric constant of the solvent medium. So further, this is z is equal to 4. Okay, that means greater the charges, greater will the electric field on the ion created by the ion, and more solvent molecules will be oriented in a particular direction, and for a larger distance the solvent molecule should have a lesser value, near about 1.78. Okay, this is the sigmoid type of curve, S-shaped curve. Okay, and this graph is talking about the differential dielectric constant as a function of distance from the ion. That means your dielectric constant value D. Oh, okay, we have represented by E. E, also epsilon, is a function of distance from the ion. The distance from the ion is greater, obviously the value of dielectric constant will also be larger. Okay, now we will now plot the graph based upon this free energy expression. Okay, my line is dead, but we can take scale. So in the y-axis, I will take free energy increase, and this is represented in kilocalorie per mole. And in the x-axis, we will consider the distance between the ions, which is in angstrom unit. Okay, so 1, 2, 3, 4, 5, 10, 20, 30, 40, 50, and so forth. So here gives free effectivation. This is ZA ZB E square NA by epsilon DAB. DAB is the distance between the ions. E epsilon is the dielectric constant value. So if the dielectric constant is kept constant, that means continuous solvent. That means we have considered the solvent to be distributed evenly and uniformly. Therefore, the dielectric constant would have same value. So, if dielectric constant does not changes with time, with time, then obviously there will be only effect of DAB will be. That means as the DAB decreases, what would happen to the free energy of dissipation? It will increase. So from here we are starting the plot. That means when the distance is larger between the ions, the free energy will be smaller. As delta G activation is inversely proportional to DAB, distance between the two ions. So when the distance between the two ions decreases, the free energy of activation increases. So I can write the plot will be look like this. There will be linear plot as there is no variation in dielectric constant is observed, and at last we can assume that will touch at the y-axis and cut at the y-axis. But actually in the real world, epsilon changes continuously. At every point the dielectric constant value is not similar. Near to the ion, the solvent would have very less value, but at far away from the ion, the dielectric constant have larger value. So these do have an effect on that. That is, your delta G activation is inversely proportional to the dielectric constant, and the value of dielectric constant is larger when the distance between the ions or solvent molecules and the ions is larger. But when the ions are made closer to each other, the solvent will become experiencing more and more electric field. They can orient themselves in a proper direction. Therefore, slowly the dielectric constant value will decrease and the Gibbs free energy value will increase. But when the ion is present very close to each other, then the solvent molecule which is present very close to ions, they will experience the maximum electric field, and therefore at that period of time the epsilon value will tends to 0. Therefore 1 by 0, that means tends to infinity. Therefore free energy of the system will increase to very large limit. That means we need to supply very large amount of energy. Therefore we cannot, it is very difficult to bring the ions closer to each other. Therefore actually the plot is looking like this. This is the actual plot, and here the free energy of the system actually increases to a infinite value. So here when dielectric constant is varied, here when dielectric constant is not varied. Again I am telling you why it is reaches to infinite position, because as we decrease the distance between the ions, the solvent molecules associated with the ions experiences larger electric field. They are under the action of larger electric field, the solvent molecules get oriented themselves. Therefore the dielectric constant value will decreases, and when the distance between the ion and solvent molecule is very less, then the dielectric constant will decreases near to about 0, decreases to very small value. Therefore, as delta G activation is inversely proportional to the dielectric constant value, so when it decreases to 0, then 1 by 0 is nothing but infinite. Therefore, the free energy of activation will become infinite in nature. Therefore, we can say that it is very difficult to bring the ion closer to each other, because we need to supply infinite amount of energy. As infinite amount of energy cannot be supplied, therefore it will be become very much difficult to bring this ion to this particular distance closer. Okay, and so for today this much only, for this class this much only will, and we have discussed the ionic reaction. We have completed all the aspects of the ionic reactions: the double sphere model, the single sphere model, the frequency factor, the free energy factor, the different consequences of ionic reaction. I hope you have understood well. If you have not understood the things which I have told in this lecture or in the previous lectures, you can just pause the video, you can just repeat the video, you can learn it. Okay, thank you so much for this class. This much only. We will meet in the next class soon.